So welcome for the fifth part of the class, that is kinetic theory of gases and the thermodynamics, and this is the last one. So we will finish this our discussions here. So regarding this, first is the second law of thermodynamics is a statement about which process occur and which do not. So the previously we discussed about the first law of thermodynamics. Now the second law of thermodynamics is basically this is nothing but I already told you that it is the expressions, or I can say the conservation of energy basically. So there are many ways to state the second law. One is the way is the heat can flow spontaneously from a hot object to the cold object. So it will not flow spontaneously from a cold object to a hot object. So the reverse is not possible. That is the second law of thermodynamics. A device which transforms heat into work is called the heat engine. So here we are basically from the second law of thermodynamics is given us an idea about the heat engine, and this happens in a cyclic process, and this is basically Carnot cycle that we will discuss in this slide. So heat engines require, what is the heat engines requires? Here it is just mentioned that heat engines requires a hot reservoir that will supply the energy, and a cold reservoir that is basically to take the excess energy. So there is an exchange of energy from hot to cold, but the vice versa if we want to do, then it will different. So that's why the statement it is given, heat can flow spontaneously from a hot object to a cold one, but the reverse is not possible. Okay, so next is the QH is defined as positive and QC is defined as negative. Okay, now this is a system that is basically showing, it is not my slides, I'm just getting it from NASA. That second law of thermodynamics is basically given here. I'm taking it because it is a very good way of explain the fact that what is happening here. You can see the Glean Research Center at NASA, that is just showing that T1 and T2, that is T1 is the hot reservoir and T2 is the cold reservoir, and there the heat transfer is happening del Q. Then we can write a new term. I am introducing a new term that is called the entropy. So what is entropy, right? So entropy mathematical expression is del Q by T. So amount of heat, change in amount of heat of the systems divided by the temperature, right? But actually or conceptually, what is the things? So entropy is basically increasing, means it will go to the unequilibrium state. Okay, so the natural process that starts in one equilibrium state and ends to in another will go to in the direction that causes the entropy of the system plus the environment to increase for an irreversible process. So actually if it is a reversible process, then the entropy is the same. So like in our universe, what is happening? That entropy is increasing. That's why we are going to unequilibrium state. From equilibrium state we are going to unequilibrium state. You can see the agitations in every field is happening. This is one of the example. Similarly, like entropy means if we will perturb or disturb the systems, that means the entropy of the system will increase. Okay. Now I told you that Carnot cycle. So this is a Carnot cycle where this is very interesting to explain. I am just explaining here one by one. You see that there is two curves. One is, it is the PV curve. Here one part is basically suppose it is started from 1 and then it is coming to 2. What is the difference here? The pressure and volume is changing. Pressure is decreasing, volume is increasing, and volume is increasing means what? The work done is happening, right? Work done is happening. So in this case, what is happening, that we are giving the energy from the outside Q. So it is work done on the system. Work done on the system. So we are working on the system. So this is T1. In this case, T1 is it is an isothermal process that we already discussed, the quasi-static process. This is a quasi-static process. So then T1 is basically here, T1 is greater than T2. Now you see 2 to 3. What is happening here? When we are, so our initial state is 1, final state is 2. This is isothermal process. And when we are considering 2 to 3, at that time what is happening? Actually, there is no change in the pressure is changing, but volume is also changing, but very little. So here there is no work done. So if you will see that curve A is equal to 1 to 2, that is isothermal expansion. At TH, I told you it is work done on the gas, right? And similarly, curve B 2 to 3, that is adiabatic expansion. So work done by the gas, this is work done by the gas. There is also some work done, and that is adiabatic because it is in real case. So real gas. So that is, it is adiabatic. Adiabatic means 2 to 3. Here the temperature and the pressure and volume is changing, but the temperature is also changing. So we cannot say it is quasi-static process. So that is it. That's why it is not isothermal, this is adiabatic. But why I am saying it is adiabatic expansion? Because work done by the gas. So that's why it is called the adiabatic expansion. Next, the curve C. Curve C is basically 3 to 4, that is isothermal compression. Why it is isothermal compression? Because the temperature is the same, but what is happening here? The pressure is decreasing. So it is a compression systems. So pressure is decreasing, right? Pressure is decreasing. No, pressure is not decreasing, the volume is basically decreasing. So that's why it is compression, right? Similarly, there is the curve D is basically this one, the 4 to 1. So here it is adiabatic expansion, this one is the adiabatic compression. So work done by the gas. So work done on the gas and work done by the gas. Here the 4 part is basically clearly understandable. That is, I just explained here. Now area under PV curve. What is area? Area under the PV curve represents the quality of the work done on the cycle. So work done on the cycle means what? That is actually this part is basically, you can see that the area under the PV curve represents the quality of the work done in a cycle. This is a cycle which we discussed here. It is a cycle, right? This 1 to 2, 2 to 3, 3 to 4, 4 to 1. That means it is initial stage and the final stage, the last stage is also in the 1. So that's why it is basically the cycle. So here the area under PV curve represents the quality of the work. When the curve goes to right to left, that means 1 to 2, the work is negative. The area enclosed by the 4 curves represents the net work done, right? Net work done, the net work done on the system. Okay, so the net work done by the engine in one cycle. So that part is basically area under PV curve. So what are the practical uses in automobile engines? That is, I told you the steam engine. We are started from the steam engine, and after that we are getting the diesel engine, then electric automobile engines, all the automobile engines, the refrigerators, air conditioners, all work on the principles laid out by the second law of thermodynamics, because here the exchange of heat. Due to the exchange of heat, there is a expansion and the compression. They both are happening, and this is isothermal. First is the isothermal expansion, and then after that there is adiabatic expansion, then isothermal compression, and then this is the adiabatic compression. So we can start from 1 and then we are coming back 1 to 2, 2 to 3, 3 to 4, 4 to 1, right? So this is the way of just understanding. Now ever wonder why you cannot cool your keychain in the hot summer by leaving the refrigerator door open? That is a very interesting question in my opinion, that if we open, suppose I am feeling very hot during the summer, and at that time if I'll just open the refrigerator door, whether we can cool our system? The answer is no, because the thermodynamical systems, it is violating the thermodynamical systems and the surroundings. There is a boundary, so this boundary we are avoiding. So when the systems, actually what is happening here, that when the systems feel the air coming off the back, you heat the air outside to the cool and the air inside. So that is the reason, that's why we cannot able to do these things. The same way, suppose we are inside the system. Suppose I am inside the system, and actually in the refrigerator, if you touch the side part, then you can feel hot. So but if you just touch inside the refrigerator, that means in the thermodynamical systems, then you can feel cold. So that is the difference, that the cold means another part should be hot, and so that's why it is in the surroundings it cannot be done. So like when we are using the AC, the air condition in the room, but if I'll just open it, suddenly this cold part is gone because it is radiating to the surroundings, because the boundary is open, there is no boundary. So you have to seal it such that it will be isolated from the surroundings. The thermodynamical system should be isolated from the surroundings. That is important. Now the biological thermodynamics. Now I am just using I am just discussing here the biological thermodynamics. This is maybe important because the concerns itself with the study of internal biochemical dynamics. Here what is the things, the ATP hydrolysis, the adenosine triphosphate hydrolysis, protein stability, as well as the DNA binding, and also the membrane diffusion. So enzyme kinetics and other essential energy control pathways is also involved here. So this is the thermodynamics. Also it is not only the systems like automobile engineering or the other part, but it is also important in our biological systems. That is somewhere it is just given here, and most of the chemistry in living systems is the result of interplay of electrons in the outer orbit of hydrogen, carbon, nitrogen, oxygen, phosphorus and sulfur. So actually our body is constituted of all the these chemicals, the mainly is the CHNO. So that's why this is very important, that the living systems the result of interplay of the electrons. So here I'm just giving some of the electronegativity, that is the tendency of an atom to attract an electron. F is the most electronegative element, but in biological system O is the most electronegative atom. So anyway, this is the electronegativity, and the biological systems are catalyzed by enzymes and involve the lone pair of electron NOP. So the complex reactions of a particular group of atoms is different. So here the energy of the chemical reactions we should know, because the second law of thermodynamics is basically it is an amount of energy capable of doing work, that is the free energy during a reactions at constant temperature and pressure. When a reaction proceeds with release of free energy, the free energy change del G has a negative value, and the reaction is called exergonic. So exergonic means opposite is endergonic, means in this case the energy is coming out, and that's why it is called the free energy. Now enthalpy is the total energy of the systems. And next is the entropy. I already discussed about this, that it is a quantitative expression for the randomness or disorders of the systems. That I told you that when we are considering this one, then the entropy, then it is actually it is it involves the randomness. It increases the randomness of the systems. So del G means what? The free energy, that is del U, and del H is the del Q. Q means the total amount, that is enthalpy, total amount of energy, minus T del S, that means dq. Okay, so this is the relation between the free energy, enthalpy, and the entropy of the systems. So next we have the cells is in isothermal systems. They function at constant temperature, and we are just giving here the process. We know that there is a two process, one is anabolism and catabolism. So both are plants, are heterotrophic cells. There is ATP. When you know that the energy is basically from adenosine triphosphate, it will be for in future we are getting from adenosine diphosphate with, and when it will store the energy, then it will come to adenosine triphosphate, ATP. So ADP plus energy is equal to ATP. So this is called the anabolism. And when the catabolism means when the energy ATP from ATP to it will come back to the ADP. So it will release the energy. And whatever we will do the work, that is basically related with these two terms, and the catabolism and the anabolism. And it is also kinds of energy systems, right? So this is the examples, I mean the definition of the same, to synthesize various compound and ingredients, and this process is called the anabolism, right? So this is the concept with the biological systems also. And now it is just given the energy containing nutrients like carbohydrates, fats, proteins, that is we are taking it. And then I told you already ATP, ADP, adenosine diphosphate, HPO4, NAD, NADP. This is all the chemicals, different chemicals, and then the catabolisms. Then it will just chemical gain the energy, and energy depleted in the end products with carbon dioxide, water, and ammonia. This is the inorganic part. And next is the anabolisms, where the cell micromolecules, we can get it from the proteins. So these are the actually the part of the systems which I am just discussing, because we know that the biological systems also do the thermodynamics. They are also following the thermodynamics. So it is a great, I mean in my opinion, it is a good examples of these things. So well, I'm just concluding here, and in future if you need more informations, you can reach me. I have given my mail ID, that is Professor Somnath, professorsomnath@gmail.com. Thank you all for your patience, and here I'm concluding the session.